So to kick things off, I'd like to open this session with a question of my own. This goes out to both Prof. Ingersoll and Ms. Steadman. Many of us here are middle and high school students, so all we see in the news is what happens after a mission launches. Could you tell us very briefly how a mission comes to be, from idea to design to choice of instruments to launch?
How does a mission come to be? Was that the question?
Yes.
It really, of course, Kim told you how the mission proceeds and how the scientific observations are designed, but before that, there's a lot of planning, and the first step is real, at least in the United States, which is what I know the most about, but in many other countries, there are a lot of spacefaring countries, as you know, but in each country, a group of usually scientists, but sometimes they're politicians and business people, but some influential group says, we've got a great idea that will appeal to people and excite them, and so far it's always been, they go to their government and say, do you think, would you pay for this mission? And here's the wonderful things that will happen. It'll give our country national prestige, it'll make people happy, and it'll be in the newspapers, and it will educate people about our universe. And then there's sort of a political process where people say, okay, we've got a certain limited amount of money to spend. Is this where we want to go, and is this the space mission that we want? And in the case of Cassini, the answer was yes. And so Cassini was born when we started to get the funding to build it. And then there was a whole process of engineers and scientists trying to decide, well, what's practical, what do we want to do? And you can't do that, it costs too much, or it's too dangerous, or it might wreck the spacecraft, or yes, that's a great idea, let's build that. And slowly the design takes shape, and then you launch it, and then Kim takes over and flies it. So it's a long process.
Yeah. When did Cassini start being planned? In like the 70s?
80s, early 80s.
Early 80s.
Yep. And I remember the process it was not called Cassini, it was called the Saturn Orbiter with Probe.
Well, and then for a while it was two spacecraft, Craft Cassini.
It was Craft Cassini, but it evolved its name.
Yeah.
Okay, could we have a question from the floor, please? If you have a question, you can press the mic, then you can. Any questions? Yeah.
How long will the nuclear reactors on the spacecraft last? Because the program that we watched said the mission will end sometime in 2017. Is it possible to go beyond that date?
It's not possible to go beyond 2017, but we don't have actual nuclear reactors on the spacecraft. We have plutonium batteries. So we have plutonium that's decaying, and as it decays, it puts out heat. We turn the heat into the power for the spacecraft. But that's not our limiting factor. In 2017, we're going to be out of propellant. So we won't be able to steer the spacecraft anymore. We won't be able to control where the spacecraft goes. And so that's why we can't go past 2017. And what we don't want to do is we don't want our spacecraft just going off willy-nilly and accidentally crashing into one of these wonderful moons that we would like to explore later. So we don't want to crash into Enceladus or into Titan. So that's why we're taking the spacecraft and depositing it into Saturn.
Thank you.
Any other questions?
Doesn't seem to be working on you.
Then to come up to the front.
Yeah. Okay, so I have extreme interest in aeronautics, and people do think that JPL only has a certain function in designing spacecraft. Are there any other important functions that JPL does serve?
Science.
Yeah, excuse me. Yeah, there's a lot of science that goes on here. A lot of, there's a whole group that just does artificial intelligence research and study. So the spacecraft work that we do, of course, is what usually puts us on the news. But there's also a lot of, when there's an earthquake out here, JPL is always on the news because we have a lot of geological scientists at JPL, and they work on not only just spacecrafts that go out into the solar system, there's a lot of Earth observing spacecrafts that we build or that our scientists work on. So and we also work on just aerodynamics and things like that. So JPL is very diverse.
Thank you. Now we have a question which is submitted by Venkata Partni Rajesh Kannan Sabari Venkat. And his question is, how can I become a scientist in NASA?
That's you.
It's very hard to control your career. But you first have to love what you're doing, and if you love science and you love engineering, and you're willing to work hard because those fields require a lot of training, and you don't get distracted by something that's even more exciting along the way, you might wind up to be a aeronautical engineer or a space scientist. But I warn you, there's a lot of interesting stuff out there, and you may find some other technical field that's even more interesting and exciting and that you love even more. And it's really not a warning at all. It's just, I would say, work hard and take advantage of the opportunities as they come along.
Do you have any other questions?
Are there any other planning for the, like Saturn or Titan, any other space aircraft are they going to launch off, or is there any designing or simulation going on?
Go.
Well, right now I don't think we have anything going to Saturn, but we do have Juno going to Europa. And
Juno's going to Jupiter.
oh, I'm sorry, yeah. We don't have anything going to Saturn. Yeah. And we also have New Horizons going to Pluto. And we have Dawn going to how do you say the name of that? Ceres? All right, so we have a lot going on, but right now, nothing going to Titan. There's been several things proposed to go to Titan, but they haven't gotten the funding yet.
Yeah, they say that Pluto is not a planet, but it's a dwarf planet. So how can you launch a spacecraft over there, but it always orbits around right? Over there, it's very dark and it's very cold over there. And it's very dark, you can't. The spacecraft can't even see Pluto, and it's very tiny that it can't be seen.
Are you asking how does the mission work? How does it take pictures of Pluto when it's so far from the sun? Is that the question?
Yeah.
How does it send the data back?
Yeah.
Is that the question?
Yeah.
Well, the New Horizons spacecraft is a fairly small spacecraft. In other words, it's not very big, not very massive. And they put it on a very big rocket, and they got that spacecraft moving very fast, and so relatively speaking, it was a very fast trip out there. And they have very sensitive cameras that can take images even in the low light levels. So there's nothing magic about it. It's just good engineering and good planning. And they have the same kind of nuclear power. And they're not nuclear reactors, but it's just radioactivity that's slowly turning into heat, and you use that heat to power the instruments. And then you have a very good antenna to send the data back to Earth.
Now, they're not going into orbit, are they? Isn't it just a flyby?
Just a flyby.
Yeah, it's just a flyby, so they won't go into orbit. It would take a lot of fuel to slow down enough to be captured into Pluto's orbit.
That's a problem, is slowing down.
Mm-hmm.
It's a problem to speed up and get there.
Yep, it's a problem to slow down once you get there.
One idea that has never been tried, but at least in principle you could do it, if you have a thick enough atmosphere like Neptune, which is out close to Pluto, you could dip into Neptune's atmosphere and slow down, but if you did it just right, you could come out again at a much slower speed and not get burned up in Neptune. You could just use that one pass through the atmosphere to go into orbit around Neptune, or do whatever you wanted after that. But it requires very clever engineering.
Right, and if you're wrong, you skip off or burn up.
So,
Yeah.
Thank you very much. I believe Prof. Ingersoll answered just now how much has the public benefited from new discoveries. But Chloe has another question, which is there real-life application of knowledge obtained from these missions?
excuse me, is there what kind of knowledge?
Is there a real-life application of knowledge which is obtained from these missions?
It's just one word, is it?
Real life
life
application.
Yeah.
application. What would an example of real life application of knowledge? I would not say that space exploration has led to better gadgets that we can use on Earth. Or gadget is a little thing like your pocket calculator. Now, on the other hand, space exploration has made us it's helped us become a technical species. Meeting these terrific challenges of space as a human race has led to our becoming a technical people. And that is, and of course you can think of many, many things that our technology has given us. And part of that is because of the excitement of exploring space has led people into technical careers and led students like you into technical careers. And so I would say in that sense, there's lots of real life applications of space exploration.
Thank you. Does the floor have any other questions? Yeah. Sorry.
Hi, I have a question about Titan. So far from all the data that you've collected and all the images you've seen, there's possibly a sort of organic environment on that moon. And so what are the, roughly from all the information that you've garnered so far, what are the possibilities that traces of life exist on Titan?
When we're sitting around drinking coffee or beer or whatever we drink. We divide into two camps. One is the Enceladus camp and one is the Titan camp. And Titan has the advantage that you have this rich organic chemistry, nitrogen and carbon and hydrogen and so on. But it has a disadvantage that it's very cold. And we don't know how warm it is inside Titan. But the surface of Titan is certainly cold. Now, Enceladus, we have water, which is a big help, and there's good evidence that the inside of Enceladus is warm because the water is coming out in these plumes, and if it was just solid cold ice, you wouldn't get any plumes. So the disadvantage of life or the unlikelihood, life is less likely to, at least life as we know it, that's all we can say. Life as we know it, which uses water as a solid, for solutions, that would not work at the surface of Titan because it's too cold and the water is all frozen. Now, down inside those moons, if there's warm rock, it's another story, but then you don't have sunlight. So I think you have to stretch the idea of life beyond Earth-type life and imagine a life living in liquid methane. But we don't know enough about the origin of life on Earth to really answer that question right now. I guess that's a fair statement. There's lots we don't know about the origin of life.
Thank you.
You want to come up to the front?
Hi. I just wanted to ask if you are doing this space exploration in collaboration with any other nation, or is it predominantly driven by the NASA's vision, or you have any other ways of tapping on the knowledge from other space exploring countries?
Well, the Huygens probe was actually built by the European Space Agency. Cassini just gave them a ride out there. And most of the instruments on Cassini, several of them are they were built and they're operated by people in other countries. I know that is it the magnetometer that's located in England? And then CDA, they're in Germany. So we have scientists all over the world that collaborated on helping design and build these instruments, and then they were delivered to JPL to be put on Cassini. So there's a lot of international collaboration. In fact, Cassini just had a meeting over in Rome with all the scientists, and they have a meeting once a year in Europe because there's so many of the scientists that are based in Europe.
I'm really looking forward to the day when space becomes truly international. It's not just a partnership between North America and Europe, and because after all, China and India have launched satellites, and I would be just overjoyed to hear that Singapore was launching its satellite, and I hope soon we get to a point where the space missions are truly international, because that will do a lot for life on Earth in terms of bringing us all together.
Other people? Yep.
Guys, one thing, can you please turn off your mics, because I think only one mic works down here at one time. So after you finish talking, can you please turn off your mic?
Okay. Okay. Does it work?
Yes.
Okay.
So spacecrafts like Voyager move out of the solar system. May I know what is the main aim of these these spacecraft which move out of the solar system, and what do they do in Milky Way galaxy?
Well, they're just sending back, not many of their science instruments work anymore, and they left the solar system. That wasn't, what they were designed for, but once they finished all their flybys in our solar system, they just kept going because there's no way to really stop them. And so, I don't know all the instruments that actually work on Voyager anymore.
You got to ask, what do you mean, what does one mean when one says you leave the solar system? Is there a boundary? And yes, there is a boundary. It's called the bow shock. And we'll stick with the bow shock. But here's an example. If you have an empty sink and you suddenly turn on a faucet that sprays water down into that empty sink, a ring of fluid will develop where on the outside there's deeper water, and then where the water from the faucet is coming down hard and it's spreading out to meet that deeper water, and that ring grows and grows and grows until finally it disappears and you just start filling up the sink. Well, the water inside that ring is like our solar system, and it's the deeper water outside is like the gas between the stars, and that boundary between the rapidly moving outward fluid inside, that's the solar wind, and the boundary with the fluid outside, which is just the gas between the stars, that's called the bow shock, and end of the solar, I don't even know what it's called. There's several boundaries out there. And Voyager has passed through that boundary and is now sampling the gas between the stars rather than the gas from our own sun. And we're learning what it's made of. We're learning basically what is out there. And of course, when a new star forms, it's gathering up that gas between the stars, and so that's how the sun formed, was by gathering up that gas between the stars. And so it's very interesting to sample that gas, because it tells us about the origin of our own solar system.
You have a question?
Hello. With reference to Prof. Ingersoll's response just now about Titan, could I ask how all the methane and hydrocarbons got into Titan in the first place?
Good question.
That's a really good question.
How did the methane and hydrocarbons get there in the first place? Well, hydrogen, carbon, oxygen, nitrogen are some of the most common elements in the sun. And so, from studying the planets and meteorites and comets, and also studying the gaseous disks around other stars, we have a picture of how stars and planets form. And the picture goes sort of like this, that initially everything is made out of the same mixture. And so initially there was mostly hydrogen, there was some helium, and then there was carbon and oxygen. And as you cool that mixture down, The carbon, because it's dominantly hydrogen, the carbon will unite as you cool it down. It will unite with the hydrogen to make methane. Methane is 1 carbon and 4 hydrogens. The oxygen will unite with the hydrogen to make H2O, to make water, and nitrogen will make ammonia, and so on. The helium is a non-reactive gas, so it just stays as it is. But as you cool that initial material down, you naturally make methane. And if you're too close to the sun, that methane gets boiled away in a sense. But if you're far enough out, maybe out at the orbit of Saturn, the methane can get trapped. And so the idea is that the methane was there when Titan formed, as everything as the solar system cooled down. Of course, we weren't there to document it, but there's all this indirect evidence that these primitive compounds were there right at the start.
Thank you.
We have a question from Joel. What is the biggest problem studying Titan?
The biggest problem.
You can't see through the clouds. You need, well, you can barely see through the clouds. Radar is very useful because the radio wave penetrates through the clouds and bounces off the surface, and that's how we can take images from the orbiter. The other way to see the surface is to send a probe down, and we did that, but it was only one place. So I'd say the fact that it's covered with clouds is a big problem. That's the biggest one I can think of.
Yeah, me too. Well, and it's hard to get to Titan. So
it's a long way.
Well, and since we're in orbit around Saturn, we just kind of go really fast by Titan. So we don't get a lot of actual time close to Titan.
Do you all have any other?
Hi. I have a question with regards to the Curiosity rover, the Mars Science Laboratory. I understand that Ms. Steadman, you worked on the project. My friends and I were doing a bit of research on the Curiosity rover, and we stumbled across a few articles with regards to how there was a surprising amount of considerable damage done to the wheels, the aluminum wheels on the rover. So I'd just like to ask, in the greater context of space exploration and in the engineering, from an engineering perspective, how difficult is it to simulate or predict the environments that the equipment that you send off Earth will experience in these planets, considering the amount of distance between us and the planets? Not just that, but the amount of distance between the planets themselves.
Well, the wheels, because this is our third rover that we've sent to Mars, and with the Mars exploration rovers, with Opportunity and Spirit, one of the problems that they had was that their wheels, the way they were designed, if they got into sand, a really sandy area, then the wheels would get embedded. And so when they designed the wheels for the Mars Curiosity rover, they designed the wheels so that they were a broader base and that they could go over sand a lot easier. But the problem was that the wheels are very large. The rover is very large. It's the size of a Mini Cooper. But they made the wheels really thin because they went on the experience from the previous two rovers. And the previous two rovers had gone a great distance, and so we thought we had a lot of experience with what we were going to see when Curiosity landed. But when Curiosity landed, she landed in an area that was quite different. Whereas before, when Opportunity and Spirit would run into a rock, the rock would fall over and they would just, keep going over the top of it. But what we ended up finding with Curiosity was we had a lot of embedded rocks that were very sharp. And so as we went over these embedded sharp rocks, they put holes in our wheels. And so what we've done is we've taken that knowledge, and in our test beds at JPL, we've put the same kind of rocks that we're hitting into, and we're testing in the wheels there. So now we can, when we go to drive the Curiosity rover, we can look at the area around us, and since we have a lot more experience now, we can say, well, we don't want to go there because those rocks would damage the wheels more, and we want to go over here where it's safer. So we have what we call red terrain that we don't drive through. Another thing that we're doing is we're driving the rover backwards a lot, because if you've ever pulled your luggage and you've tried to go over a bump with your luggage, it's a lot easier to pull your luggage over it than to push your luggage over the bump. And so that's helped us with our wheel wear. And I'm not sure the distance is the problem when you're planning, because like for Mars we had a lot of information because we have a lot of orbiters, and the orbiters have sent back just really great data about what the surface of Mars looks like. I think one of the questions in the sheet I got was, why didn't we send a rover to Titan? Well, until Cassini got to Titan, like Dr. Ingersoll said, we had never seen the surface of Titan. We have no idea what it looks like, so there's no way we could send a rover there until now we have data from Cassini, and maybe that's a possibility in the future. But the problem is operating these rovers, because from Earth to Mars it takes us between 10 and 30 minutes, depending on where Mars is versus Earth, to send a signal out there. So we have to have really good fault protection software and really good artificial intelligence on the rover, so that if we send the rover a command to drive somewhere that's not safe, then the rover will be able to look at her surroundings and say that's not safe and stop. And so that's the real challenge there, is just making sure that you give the rover something that she can actually do without harming herself. Does that answer everything?
Yes, thank you.
Does anyone else have questions? Do you want to ask one?
This is a follow-up question to Professor Ingersoll's comment about sending a probe to the surface. Now that you know that there's liquid water under the frozen surface, is there a possibility of a future mission landing a probe, trying to bore through the ice to do a direct sampling of the water underneath, or is the ice too thick?
Well, that question applies both to Jupiter's moon, Europa, and Saturn's moon, Enceladus. Can we drill through the ice? It's going to be tough. It would be tough. But there's lots we can learn before we drill. We can send radars down that penetrate the ice. Radars have been used to penetrate the ice caps on Mars, for instance, and for that matter, the ice caps on Earth. And from the gravity, we can tell the density of what's underneath, and we can tell whether it's rock or ice or liquid just from the gravity. We can also measure the heat coming out of the cracks. We've been trying to do that and doing a good job, but we can't really fly close enough to measure in detail where the hot spots are. And of course, when we're really close, or if we're on a rover on the surface, we can find exactly where the vents are and what's really coming out of them. So just being close, being on the surface, having the right instruments. Cassini has a wonderful suite of instruments, but we couldn't anticipate what we would find, so there's lots of instruments we would add, and there's lots to do before we try and drill.
The gentleman at the back? Yeah.
Hi, may I know what are some of the features of the Cassini spacecraft which actually protect it from the harsh conditions of space?
Well, Cassini has heaters on her so that the instruments that need to be warm can be warm. And we have protection on the spacecraft, which we call thermal blankets, which protects it from the cold and also protects it from micrometeoroids, because that's the biggest danger to the Cassini spacecraft. It's vast, but it's also very dusty. And so it wouldn't take a particle very large as fast as Cassini's going, because when she flies by, Alan Lee will probably have to correct me here, but I know when we go by Titan, a lot of times we're going like 5 or 6 kilometers per second. And when we go by Enceladus, I think it's more like 13 or 14 kilometers per second. We're going very fast. And so it wouldn't take a very large object to just absolutely destroy our spacecraft.
Like a millimeter.
Yeah, it's just very,
Millimeter.
I know it's ridiculously small. So that's our biggest fear. So some of our scientists do a lot of work trying to figure out where these dust hazards, that's what we call them, dust hazards are, so that we can turn the spacecraft in a certain, orientation to protect our sensitive instruments and our electronics on board.
Did anyone else have questions? Do you want to ask?
Hi. How does a spacecraft navigate through space?
How does a spacecraft navigate through space?
Yes. To get the.
Is that the question?
Yeah. I mean, how does the Cassini spacecraft get to the Titan from Earth?
Well, we have some very smart people called navigators, and they plan our path, and they tell us which way we need to go to stay on the path, and then we fire our engines. We have a main engine, which is a huge engine, which gives us about 400 newtons of thrust, and then we have some small little RCS thrusters. And so every time we have a targeted Titan flyby, Titan's sort of our anchor, but every time we have a targeted Titan flyby, we have 3 what we call orbit trim maneuvers. So we're constantly changing our path so that we'll stay in our trajectory. Sort of like when you drive your car. You push down the gas pedal and go when you need to go, and if you need to speed up, you speed up, and if you need to make a left-hand turn, you turn your car and go left. And the same thing with Cassini. When we, the navigators figure out to stay on our trajectory, at certain times we need to burn our engines, we need this much of a delta V, and we need the spacecraft pointed in this direction, and that's how we do it. There's a whole team that their only job is to keep us on our trajectory.
Thank you.
We do that, the engineers do that, all those maneuvers, with surprisingly little fuel usage. And they do it by using Titan, in this case, as a slingshot. So that if you want to change direction, you fly very close to Titan, and you let Titan's gravity send you off where you want to go. In fact, the Cassini used Jupiter as a slingshot to get out to Saturn, and probably robbed Jupiter of a tiny, tiny, tiny amount of its orbital motion around the Sun. But these gravity assists make it much cheaper. You don't need as much gas in your tank when you use gravity assists.
Yeah, if Titan didn't have a big, thick atmosphere, we wouldn't have been able to have as much of an extended mission as we do.
Now we have a question from Vera. What is the most interesting or memorable events that occurred in your line of work?
What a simple question.
I'll tell you, in the exploration of planets, I'd say the discovery, now it's more than 10 years ago, that other stars have planets going around them. And that number, it was one in, I don't know, it's 20 years now, 1995. There was one, that was the first star with another planet, another star besides the sun with planet going around it. And then that became 2, and then 4, and then 8 and 16, and that doubling time is about every 2 years, and now we've got over 1,000 other planets, and we can begin to extrapolate. Since we've only sampled a few stars, we can say, okay, on what fraction of the stars we've sampled have planets? And it looks like half the stars, at least in the galaxy, have planets going around them. And to me, that's the most exciting thing, because it says with that many planets, some are too near their stars to have life, but some of the others are the right distance. It says that life could have formed in many places outside the solar system. So to me, that's the most exciting discovery in the last, say, 20 years.
ask yours?
Hi. Seeing as how Titan's geological landscape is remarkably similar to that of an early Earth, what sort of weather phenomena do you think has shaped these landforms? Because Titan seems to have a lot of familiar landforms such as rivers, lakes, and seas. So what sort of processes have allowed such landforms to come into shape on Titan?
Really, Titan is a cold place. Let's not forget that. So water is not going to make rivers, lakes, and seas. You need another liquid. And fortunately for Titan, that liquid was there. It was liquid methane. And the only reason methane is a liquid on Titan is because it's cold. And so given that there was another liquid available, not water, it was just inevitable that there would be rivers, lakes, and seas. On the other hand, one of the surprises is that the weather there is violent enough to carve deep channels because there's much less sunlight after all. And you've got to have floods to carve channels. And with that little amount of sunlight, you've got to evaporate a lot of methane, and it's all got to come down at once in a big rainstorm. And so to me, that was surprising. How could a planet, okay, so it has liquid, it's methane, but how could a planet, even if it has liquid, it's got very little energy to power those floods, and yet we see the geological evidence of the flood. So that's another question we haven't answered yet. But of course, if we knew all the answers, it wouldn't be worth exploring. So the reason we go there is to answer the old questions and discover new questions.
We have time for one last question.
Hello. What are the factors that determine if a target is important to focus on in a mission?
The process.
Can you repeat the question, please?
What are the factors that determine if a target is important to focus on in a mission?
Let me do that. Okay. Well, whenever you have a mission, you create the mission to answer certain scientific questions. And so you go after the targets that will help you answer those questions. But the interesting thing, like Dr. Ingersoll just referred to, is when we got to Saturn, we had all these lists of questions that we wanted to answer, and then as we answered some of them, of course that brought up new questions. And so what you have to do is you have to prioritize, and the scientists get together and decide that these are our priorities, the things that we really want to know. And then from there, that will tell you, then you can come up with the observations that you need, the science observations. So to answer this question, we need to look at Titan. To answer this question, we need to look at Enceladus. And so those become your primary targets. And so when you have an opportunity to either look at like Enceladus or another small moon, if you have a great opportunity at Enceladus to help answer a question or get data towards helping you answer that question, then you look there. It's all about priorities.
And some questions are just too hard.
Yeah, or you don't have the proper instruments, and so yes, you have this question, but you just have to put it on the back burner. And so then when you make the next mission, then you can design the instruments to answer that question. Just like when Voyager went by Saturn and took all these great images of Titan, they didn't realize that they wouldn't be able to see through the haze on Titan, and so they got all these wonderful images of an orange ball. So when Cassini went, she was armed with radar, she was armed with these filters on her camera so that she could see the surface. And so every mission builds on the one that's gone before it.
Thank you very much. I understand that some of you still have some burning questions, so maybe at the end, if we still have some extra time, we can direct the questions to the scientists later. So right now, thank you, Prof. Ingersoll and Ms. Steadman for joining us today. I'm sure our audience has learned a lot about Saturn and space exploration in the past hour. I'd like to invite Wei Lin to present each of you with a token of appreciation.
Thank you very much. Thank you.
Thank you.
Thank you.
And now,
Thank you for the questions.
Yes, thank you very much.
and now the moment you've all been waiting for, the winners of the Cassini Scientists for a Day essay contest. This year, we saw 43 participants from 9 schools submit their essays about the F-ring, Titan, and Saturn, and justifying why they felt the target had the most scientific merit. It was a close fight between many qualified participants, and we would like to thank everyone for their effort. First, a thank you to the schools which participated. Please send one representative to collect the certificates of participation of participants from your school. So first we have Bukit Panjang Government High. Chen, you want to? Yes, it's all on. Hwa Chong Institution. School of Science and Technology. No, I think Hwa Chong. Overhead. Singapore Polytechnic. And last but not least, Yuva Bharati International School. We also have one lucky participant who will walk away with a lucky draw packet of NASA memorabilia. Congratulations to Rasesh Savasagaran.
Thank you so much. Okay, thank you a lot.
Now, in recognition of the many high-quality essays, we'd like to present the following participants with awards of honorable mention, in no order of merit. First, we have Aditi Malkote. Fu Suying Jilan. Huang Wei. Ko Zequ. Kopati Sandeep. Carissa Lim. Raviraj Ramchandra Talgeri. Ryan To. And William Ming. We would also like to mention Rachel Teng and Tan Yixuan, who could not join us today. All the honorable mention winners can come and collect your goodie bags at the front later. And finally, the winners of the Cassini Scientist for a Day Essay Contest 2014. In third place, we have Jian Ouyang from Bukit Panjang Government High. In second place, we have Chiu Chen Ning from the School of Science and Technology, Singapore. Well done. And finally, the winner of this year's contest, we have Fong Kai Yung from Raffles Institution.
Well, this is slightly troublesome.
Thank you so much.
All winners can also get their goodie bags from the front later. Our 3 winners' essays and photos will be posted on JPL's webpage as international winners for 2014. Now we have one last award to give out, and this is the Cassini Explorer Award, given to the school with the highest total aggregate score of its participants. We had several close contenders, but this year, the award goes to Singapore Polytechnic. Thank you for your enthusiastic participation, and we hope to have your continued support. With that, we conclude the third Cassini Scientist for a Day video conference. Please do gather in the front for a group picture before we scatter. Thank you all for joining us this morning.